Welcome to Math115.com. We're moving on to continuous random variables. They're really exciting. So, continuous random variables are different than finite random variables because every single variable in finite has its own probability. In this case, there are an infinite amount of variables. So, to illustrate, we can take a number line from 0 to 10. Now, within this number line, there already are an infinite amount of numbers. So, in continuous, if someone asked you, how do you find the probability of x equaling some specific number, in this case, let's say 3. If we were to try and find this in a continuous random variable, it's impossible because what we would essentially be doing is we would be saying we would take this number 3 and divide it over an infinite amount of numbers. If we would go ahead and do that, it would be so infinitely small that it just doesn't exist. So this doesn't exist, and that would always be 0. So I'm going to explain a little bit about how you can find probabilities in continuous. If we were to take any function from 0 to 10 and graph it, something like that, you find probabilities for continuous random variables based on the area underneath the curve. Now, this is only true for PDFs, which stands for probability density functions, because the CDFs will always end in 1, the probability of 1, and the point on the graph is equal to the probability because it builds the same way as finite does. So I'm going to get into two separate types of continuous random variables that I can use to explain some of these concepts. I'm going to start off with a continuous random variable called a uniform. So for uniform random variables, we have a couple different rules. One is that everything happening within this random variable is equally likely to occur. So it's really easy to draw because it's just a horizontal line. And let's say it goes from 0 to 10. And this would be the graph of our function in this case. Now, to find the height of this line, there is an equation for it, which is 1 over b minus, I can't write, minus a. So in this case, we have 1 over 10 minus 0, so 1/10. So now the way this works is if someone wanted to ask you to find the probability that x is less than 1 or less than 2, they could ask you for the big F of x, or just f of 2, I guess, big F of x of 2, or they could ask you for the probability that x is less than or equal to 2. So if we were to do that here, we would then again want to find the area underneath the curve, or this space, to find that probability. To do that, we would go ahead and put in our x value at the top over b minus a. So it would be equal to 2/10 or 20%. Pretty simple. Okay, so the two special cases for exponential, or the two special requirements for exponential random variables, is that they are time between events, so like 2 minutes between someone going to a bank, or a couple minutes before you park your car, I don't know, just time between events, always time between events. And then there's an average, and then that's the average, usually time between events, which is referred to as the alpha. So the alpha looks like this, and the alpha is the same thing as an average, as I just stated, which is the same thing as the mean, which is also the same thing as the mu character, which you might see in your homework, which is also the same thing as an expected value. So don't let any of these terms confuse you or worry you. They all mean the exact same thing, so you can use them to solve problems as such. So the exponential equations also have graphs for the PDF and the CDF versions. Now, the PDF exponential graph would look something like this, and the CDF would look like that. Again, the CDF ends in 1. Now the equations that go along with these, the PDF one is 1 over alpha times, that is a times, e to the negative x over alpha. And the CDF one is really simple, it's just 1 minus e to the negative x over alpha. So let's do a couple problems here that I've made up for these random variables. So the first one deals with a uniform random variable. And we are saying that if this equation, hold on, let me check my notes. Oh yeah, it's from 1 over 100 if 150 is less than or equal to x, which is less than or equal to 250. So they're essentially saying the function, this is the height of the graph, and it's a constant because it's a uniform random variable, and it only runs from these points, from 150 to 250. So we'll graph it up here, and this is the PDF graph of it, starting at 150, going to 250. The height of the graph is 1 over 100. Now, what we want to know in this case is we want to find the probability of E of x, which is the same thing as the average and everything else, if it's less than or equal to x, which is less than or equal to 225. So this is going to be a two-stage problem, because first we have to find out what the expected value is, or the average is, for this uniform random variable, and then we want to find the probability between those 2 points. So first let's find this point. Now the equation for the expected value for a uniform random variable is pretty simple. It's going to be the middle point along this graph. So somewhere around there. Because if it's uniform or equally likely to occur among any of those points, the center point will happen the majority of times. So we'll take both of these 2 points, the 150, and add the 250 to it, and then divide by 2 to just get a simple average, which would be the center. So we know that our expected value is going to be 200. So this is going to be our first point on the graph that we're looking for. So now we know that we're looking for the probability of 200 less than or equal to x, which is less than or equal to 225. So let's put in the 225 in here on the graph. So now we know we are looking for this space in here. One mathematical way we can do this is we can take the width of this and multiply it by the height of the graph to find the probability or the area underneath. So that's the way I'm going to go about it, just because I find it the simplest. So we'll take the 225, minus it from the 200 to get the width. So we have a width of 25, and then we'll take that and multiply it by our height here of the graph. So we have 25 times 1 over 100, which is equal to 25 over 100, or 25%. So we know that the probability of x between these 2 points is going to be 25%. Now another way to look at this problem is if we look at it in the CDF version. If we were to do it for a CDF, it would still go from the same points, but it would come up at a constant rate and end at 1. Now we can go ahead and solve this with the CDF as well, from the 200th point to the 225th point. But the difference is that when we solve it using a CDF, this point would accumulate all of these probabilities. So you would find the probability at this point here, and then subtract it from this point here on the y-axis. I think I should run through that. Okay, so if we were to do that, we would find this point.
You haven't shown the CDF formulas yet, so.
To find this point on the CDF, we would want to take this point and take the 225. Isn't it just your point minus the beginning point over the whole thing? Yeah, I'm pretty
sure. But you don't want to show it to them like that because they'll have no idea what you're doing.
That's true. So the CDF formulas for these, for this one is going to be x minus a over your b minus a. This will give you your base and then your points. So in this case, our x value, let's start with the 225, is equal to 225 minus our starting point of 150 divided by the whole thing, 250 over 150. So if we subtract these, we're going to end up getting 75 over 100 or 75%. So I'm going to fill it in here. And we now know that this whole area, or the point on this graph, is 75%. But we want to find between these two areas, or these two subtracted. So then to find the next one, which would have been our average point, we'll take the same formula, the x minus a. We'll take our 200 minus a, 150 over b minus a, 250 minus 150. So then we end up getting 50 over 100, or 50%. So if I come over here, I can fill in 50%, and then all we're essentially doing is subtracting these 2 points on the graph. So there's one more step when you do it this way. We'll have to take the 0.75 minus 0.5 to equal 0.25, or 25%. So really all you're doing is finding a different way to look at and solve the same problem, whether you use the PDF or the CDF version. These are the exact same random variable, just solved differently.